All right, in this video, I'm going to be working some fundamental theorem of path integral examples, and we're going to be looking at, independence of path and finding a potential function to evaluate a path integral. So if f of x and y equals y and x, and c is a smooth curve that starts at the origin and ends at 3, 8, find the integral over c of f dotted with dr. Okay, well, I think first I'm going to check, is f conservative? Because if it is, then I can... I'm going to need it to be in order to just not know anything about the curve besides its endpoints. But I'm going to check, is my equal to nx? My is 1, derivative of this with respect to y. And then the derivative of n with respect to x is also 1, so I know it's conservative. So now I'm going to find a potential function. And I'm thinking, I think it's going to be xy, because then the derivative with respect to x would be y, and the derivative with respect to y would be x. Yeah. So f of x and y equals x times y. Okay. And that means, okay, if I want to integrate over c, f dotted with dr, well, that's just going to equal f of 3, 8 minus f of 0 and 0, because it started at the origin. That's going to be, all right, 3, 8 is 24 minus 0, 0 would be 0 times 0, and so that's going to be 24. Now C is, okay, this second one, this one bumps up the difficulty a little bit. Okay, we're going to start at the origin and go to the point 431, but it's like we're going to compute this, which is not f dot, we aren't given f, basically, is the thing. So what we're going to need to do is we're going to need to identify what is our function that we're integrating. Okay, so if I already know that f dotted with dr is equal to 6x dx minus 4z dy and negative 4y. I'll just copy it. Okay, I guess I'm assuming that it's a line with... Oh no, that's interesting. That's right, if it's... a way that you can smoothly parameterize it as a line where they're all moving with the same speed. I don't know that that's possible. I'm gonna think about this problem for a second. Okay, yeah, I was just thinking about that wrong because, dr is dx, dy, dz. I was afraid that, basically because of the partials of r of t being, even in like a line from the origin to this point being not strictly 1, but that would be if this was, dt's, I'd have to be recovering that information. I don't need that, right? I can just say that I know that f is equal to 6x negative 4z and 20z minus 4y. And then I'm going to potential function for that. That's might be a process, though. All right, so I'm going to start by saying that 6x is equal to the partial derivative of my potential function with respect to x, meaning my potential function is an antiderivative for 6x with respect to x. Okay? So I know that it's going to have a 3x squared component in it, but it will probably also have some kind of constant function of y and z as well. Okay, but hopefully that'll shake out over the next two pieces. Okay, so f is also going to be an antiderivative for negative 4z with respect to y. So that would give me something like, let's see, negative 4yz plus some other stuff that could depend on x and z both, but not y. Okay, yeah. And then also we've got f equaling an antiderivative for 20z minus 4y with respect to z. Okay, that minus 4y, that's starting to make more sense now because I'm going to see it twice. Okay, so that's going to give me 10z squared minus 4yz. Now I think, plus some constant function that could depend on both x and y. Okay, the thing that depends on both x and y, I think that's got to be the 3x squared. The other ones, I'm confident that, we'd see them in the partial derivatives if they were, like c2 of x and z is going to be the 10z squared. And then this one is the negative 4yz. So in total, at least my hypothesis is f of x and y and z is going to equal 3x squared plus 10z squared minus 4yz. And then I'm going to just quickly check by taking the partials and finding the gradient and making sure it's this. So partial with respect to x, 6x, 0, 0. Okay, feel good about that. Partial with respect to y, 0, 0, negative 4z. Okay, good. Partial with respect to z, 0, 20z, negative 4y. Yes, okay, good. Yeah, happy. All right, so this is my potential function, and now, okay, I know that the integral over curve C of f dotted with dr is going to equal this at 431 minus f of 0 and 0 and 0. And I'll plug that in. Say f of 431 is going to be 3x squared, oh boy, 1648, 10z squared, that's just 10, thankfully, negative 4yz, negative 4 times 3 times 1 is negative 12. Okay, so that's going to be 46. And then when I plug in a bunch of zeros, I'm going to get all 0. And so that's going to be 46. I like that problem. Okay. The next one is determine if this vector field is conservative, looking at a picture of it, which is, I think it's kind of not always so easy to tell if it's conservative just from looking at a picture of it. It's pretty easy to tell when it's not conservative, and that's going to be this one. Because if we can draw a closed loop over which the path integral is clearly non-zero, then we know it's not conservative, because then we could do the fundamental theorem of path integrals on that closed loop and it would come back 0. Okay, so I think what I'm going to do on this one, I can see that if I do some sort of like circular path, like this, okay, if I give the orientation that's, the way I drew it, then it would come back a positive path integral because the field lines are going with the path the whole time. If I was to use this kind of an orientation, well, I'd be going kind of against the field lines at all times, and then the path integral would come back negative. Okay, so that means that this is not conservative, right? Because the path integral on a closed loop was not 0. So now, I did choose this one because this one's one that we can look at and say, hey, this is for sure conservative. And I can say that because it's constant. Okay, so I am going to, I think maybe in one of my sections I proved this fact, but I think I'm just going to mention this now that you're watching, that any constant vector field is going to be conservative. Okay, so I'm going to say it's conservative because it's constant, and say it's, negative 1, 1. Looks like it's the same vector everywhere. Okay, so that means it's going to be conservative, and I'll prove that for you right here. That's okay, gonna prove it. Okay, this is assuming a and b are real numbers. I'm just going to exhibit a potential function. So I'm going to say f is pretty clearly equal to the gradient of g, where g of x and y is going to be, I think, ax plus by. Yeah, because the partial of this with respect to x will be a, the partial with respect to y will be b, and there you go, I've got it. Okay, so since we can cook up a potential function, that means it's conservative. Okay, so any constant vector field is going to be a conservative vector field. I've also seen an explanation of that kind of goes to the, you draw the closed loop, and like all the ones going in are balanced out by the ones going out on the other side. More geometric argument, but I think that's the clearest reason why a constant vector field is going to be conservative. I need another sheet of paper. All right. Now we're going to find the work done by F in moving an object from point P to point Q. Right? Well, it had better be a conservative force field in order for us to do this without knowing the path. So I think. Okay, these are both two-dimensional, so I'll verify it. If it's 3 dimensions, I'm probably not going to compute the curl. I'm just going to take it on faith. Okay, so let's see. My is going to equal 18x squared y. And then nx, sure enough, is going to be 18x to the 2, y to the 1. Okay, so I know it's conservative. Now my job is to find a potential function. So I'm going to say, all right, f is the gradient of function g, which is going to be my potential function, where g is, I got plenty of room here. G is an antiderivative for 9x squared y squared with respect to x. Let's believe that that's going to be, with respect to x, that would be x to the third divided by 3. That would be 3x to the 3, y to the 2, plus some constant function of y. Okay. But then at the same time, I would also have g equaling an antiderivative for 6x to the 3y minus 1 dy. Okay, and then that would tell me that g was equal to, okay, again, the 3x, wait, no, yeah. Y is going to bump up power by 1 and divide, so that will be 3x to the 3 is a constant. Y power is going to increase by 1. Antiderivative for 1 with respect to y is going to be y. And then there could be some other constant function of x. Okay, I know that that constant function of x would show up over here if it existed, so it's just going to be a constant, maybe. And then over here, that's it, that negative y. I didn't mention this, I think, the first time I computed a potential function. I think that was in problem number 2. But I was just assuming c was 0, because you can choose any of the family of potential functions that are separated by a constant. And in general, I'm just going to choose the one where c is equal to 0. So a valid potential function is g of x and y equals 3x to the 3, y to the 2 minus y plus some constant. Well, I'm going to assume that constant is 0 because I'm just using this for the fundamental theorem. And now I know that the integral of f dotted with dr, which represents the amount of work done, is going to equal g of q minus g of p. Okay, so that's going to be, when I plug in 5 and 9, all right, well, all right, yeah, I'm not going to be able to take 125 times 81 mentally. Maybe you can. I see how a person probably could. I think it might be 1125. No, that's not, no. 10,125, I don't know. Not worth it. So what we're going to do is we're going to plug in on this 3 times 5 to the 3 times 81, 3x to the 3, y to the 2, minus y. Okay, no, just, oh yeah, and I had to multiply by 3. That is, okay, so 30,366. And then when I plug in 0, I'm going to get 0. So 30,366 minus 0. That seems like a lot of work. I don't know. All right, and this one. All right, let's verify that it is conservative first, and then we'll find a potential function. So y is equal to, all right, well, this is equal to 2x y to the negative 1, so that would be negative 2x y to the negative 2. Is nx going to be that? Yeah, it'll be negative 2x on top, and then that y to the negative 2 will stay there. Okay, so that is equal to nx. Okay, now I'm going to find a potential function. So I'm going to say f is going to be the gradient of g, and g is going to be an antiderivative for (2x y to the negative 1 with respect to x. So we'll anti-differentiate with respect to x and get x squared plus some function of y. And then g is also going to be an antiderivative for negative x squared y to the negative 2 with respect to y. And then that will tell me it's going to be, all right, I'll add 1 to the power, divide it by the new power, so that'll be positive x squared y to the negative 1 plus some function of x that I would see over here if it really existed. And this constant function of y, I would see it over here if it really existed. So I'm going to say that my potential function is going to be x squared y to the negative 1. And plus some constant, which I'm going to assume is 0. Okay? Meaning that the work done, which is the integral of f dotted with dr over that curve C that starts at negative 3, 2 and ends at 1, 4, well, that's going to be g of 1 and 4 minus g of negative 3 and 2. All right, and that's going to be not nearly as difficult to compute. All right, g of 1 and 4 is going to be x squared divided by y. Okay, so 1/4. Okay. G of negative 3 and 2, negative 3 squared is 9, divided by 2 is 9/2, but I could call that 18/4, so that I could combine these and say that's negative 17 divided by 4. Now, number 5, we're going to let f be a vector field and let g be a function, be a potential function for g. Suppose the integral of f dotted with dr over curve C is 4. What's the integral over curve D of f dotted with dr? Well, that means f is conservative. It means it's independent of path. So if I'm going from P to Q, my integral is going to be 4. Okay, so that's going to be 4. Along path E, that's Q back to P. Okay, and so that's going to be negative 4. Okay. If H is a path from P to Q back to P, what is the integral of H? Over H of f dotted with dr. That's going to be a closed loop if it goes from P to Q to P. That could be like C and E, or it could be some other much longer loop. What's important is that it's closed, and an integral of a conservative vector field over a closed loop is going to be 0. Okay, so I'm just going to say that. And that's all for this problem set. So thanks for watching.